I have Maria here today. She's the last talk of the day, going to talk to us about Bayesian optimal design for Gaussian process model.
Hello, and thank you for the invitation and for organizing this workshop. Today I'm going to present our work on Bayesian optimal designs for the Gaussian process model. So this presentation is going to be about how we are going to choose the design points for the Gaussian process model. It's a joint work with Dave Woods from University of Southampton. This is an outline of my presentation. I will start with a brief introduction by giving the background and the motivation in three main research areas. So I will give examples from computer experiments, spatial data collection, and physical experiments. Then I will outline the Bayesian approach that we followed to find optimal design and describe the decision-theoretic approach that we use to derive our objective function for finding designs for prediction and estimation. Finally, I will illustrate the properties of these designs through numerical examples. So, experiments are widely used to gain understanding and improve a product or a process by applying treatments in experimental units. So we define as treatments the settings of the controllable variables that can be applied to a specific unit. So by design of experiments, we mean the active selections of these settings of the controllable variables by taking into account the uncertainty that we may have. Usually, the aim of the experiment is to collect the data, and based on this data to answer different scientific questions, and we can do that through the estimation of a statistical model. A well-chosen design can be selected to maximize the information that we are going to have from the available resources. Usually this information is measured with respect to the uncertainty about the models and its parameters. We choose to follow a Bayesian approach because before we are going to conduct any experiment, we usually have available prior information about the factors that we are going to use, their possible values and possible models that connect the inputs with the outputs. So this information may be subjective, empirical, or mechanistic. So a Bayesian approach is going to allow us to take into account all the available prior information in a coherent way, and also take into account the uncertainty about any unknown model parameters that we may have. Also, for many experiments, it's natural or even necessary to be Bayesian. The first application is in computer experiments, where computer experiments are very important in science and engineering. And the idea of computer experiments is to replace the actual physical experimentation with the computer code, and we run the computer in order to simulate the true behavior of the physical process. So, a computer code g of x is based on a mathematical model that describes the physical process, and we can use this computer code to study the relationship between inputs x and outputs y. If we want to learn the relationship about inputs x and outputs y, ideally we want to evaluate this computer code in every possible combination of inputs x. However, this is computationally infeasible, and in an analogy to the physical experiments, we choose some design points where we are going to evaluate the function g of x, and based on the data that we are going to collect, we are going to fit a statistical model. So we basically approximate the computer code by a statistical model, which is the emulator. And the most common emulator is a Gaussian process. So computer experiments can be applied, for example, in automotive industry, and this is an example from Jaguar Land Rover, where they offer a range of customizations for their models. So through a vehicle program, they can modify their car according to where in the world they are going to sell their car. So a customer can choose between seat configuration, engine, gearbox, and drive configuration, and each one of these combinations is going to create a new version of the car. So the aim is to use a computer model to predict these variants, because every variant is going to have different mass inertia properties, and they are going to lead to different ride characteristics. So it's important to find out and predict what is going to be the ride performance for these versions of the cars. The second example is from the area of spatial statistics and the typical sensor placement problem, where here we have the monitoring stations of 122 monitoring stations in Eastern USA, and the aim is to choose the best location if we want to predict the black dots here. So we have 122 candidate points indicated by open circle here, and we choose the optimal locations, which are the blue triangles. The link between spatial statistics and computer experiments is the Gaussian process model, and here the correlation function in Gaussian process model describes the spatial dependency that we have in our monitoring network. The last example is from the physical experiments, where here we want to choose the treatments that we are going to apply, for example, in a well plate, but we need to take into account some spatial or temporal trend. These kinds of experiments are typically in field trials in agriculture or in lab experiments in well plates. So the aim is to choose different treatments in each one of these wells, but we need to take into account that the wells are correlated between them and need to take into account how the correlation change according to the distance between the wells. So the Gaussian process prior is going to be assigned for the random effects for the Gaussian factors, where the Gaussian factors here is the well plates. I know that these days you have heard a lot about the Gaussian process models, but I'm going to give an overview of what a Gaussian process model is. So it's a very popular Bayesian non-parametric approach, where we consider the function g of x as a black box and all the available prior information that we have about this function is represented by a Gaussian process prior with a mean and a covariance. So any joint sample from G has a normal distribution with trend and covariance given by the formulas here. Given that we have some data, we want to update our prior beliefs, and this can be done through the posterior distribution. And if we condition to all the model parameters, it's straightforward to derive the posterior distribution, which again is a normal distribution with now a mean and a variance covariance updated. So the mean is basically the prior mean weighted with the residuals and the distance between the points that we already have in our designs and the points that we want to predict. Similarly, the sigma, the S square, takes into account the variance reduction according to the distance of the points that we already have in our design and the points that we want to predict. So, and we are going to have smaller variance for points that they are closer to the points that we want to predict. Also, we define as a noise to signal ratio tau square, the ratio between the variance of the measurement error sigma square epsilon and the scalar of the Gaussian process sigma square g. This is a very simple example of a Gaussian process. Most of you are very familiar with it, but I will just give a simple example where we assume that the true function is the sine of x, then g of x, which is the gray line here, and we assign to it a Gaussian process prior with constant mean and a square exponential correlation function. So before we having any data points, the Gaussian process means that we can have functions of any shape to represent our prior beliefs. However, we need to choose some points indicated by the circles here, and based on the data that we are going to collect on these points, we are going to have the posterior distribution, and now is the black line that has a similar shape with the sign of x. So basically, the posterior distribution assigns weights to the functions that they are go close from these points. Also, we can see that at the points where we have observations, the uncertainty drops close to 0, and at the points where we don't have any, at the areas where we don't have any points, we have wide prediction intervals, and the Gaussian process goes towards to the prior mean, which indicated by the horizontal line here. In this example, we assume that we know the correlation parameters lambda and tau square, but usually this is not the case, so we need numerical methods to evaluate them. So we are going to use empirical Bayes, where we estimate these parameters and plug into the equations, or Markov chain Monte Carlo and sequential Monte Carlo methods. So there is a growing literature in the area of design of experiments for Gaussian process models, and we can split in two cases, the model-free approach and the model-based approach. So in the model-free approach, we don't make any specific assumptions about the model that connects the input and the output, so we have the space filling designs, and we just want to spread the points or cover the area that we want to predict. The second approach is a model-based approach, where we have the designs either for prediction or for estimation, usually estimation of the correlation parameters. If the aim of the experiment is the prediction, then we have the creaking variance as objective function to minimize the creaking variance, or integrate mean square prediction error. If the aim is the estimation of the correlation parameters, we have the designs based on the entropy or the optimality. And finally, we have the sequential designs, which are very popular for optimization problems and predictions, and we want to add a point in the existing design. So now I'm going to focus on the methodology that we use to find the Bayesian optimal design, and we follow a decision-theoretic approach. So we need to define a loss function that captures the loss of making a specific decision D when the true state of nature is theta, and we have data that we have collected on specific design. So the loss function is chosen according to the aim of the experiment, and for example, we can have the square error loss that we are going to use later on, or negative log score that leads to entropy problems, and 0-1 loss. Once we can define and choose our loss function, we need to make a decision that minimizes the expected posterior loss given by this integral here. So we need to choose the base decision based on the data that we have indicated by this star, and given that we have some data, this decision may be decision for estimation or decision for prediction. However, our problem is to find the design that we are going to collect the data. So we need to derive our objective function that we are going to use to find the design. So this can be done through the Bayes risk, and is basically the loss function evaluated at the base decision, and because we don't have any data prior to the experiment, or we don't know the model parameters, we need to integrate out with respect to the data and the unknown parameters. Usually evaluate this Bayes risk is challenging because we have a high dimensional integral with respect to the data and the parameters, and also maybe we don't have in closed form the Bayes decision D star. And finally, an optimal design can be obtained by minimize the base risk. So in the rest of my presentation, I will apply the decision-theoretic approach to the problems of predictions and prediction and estimation. So usually in spatial statistics and computer experiments, the response is very complex, and for this reason we want model-free predictions. And by this we mean that we don't make strong assumptions about the underlying model, and for this reason we assign a Gaussian process prior on the unknown response function, and the correlation function allows the prediction to smoothly follow the data. So an optimal design can be obtained by minimize the prediction uncertainty. As I have mentioned before, the most popular designs are the space filling designs because they don't rely on any specific functional form between inputs and outputs, and also they allow us to have good coverage for prediction. These designs can be, for example, the maximin or minimax designs or Latin hypercube designs. But there is a connection between the space filling designs and the Gaussian process model, and especially for a Gaussian process model with constant mean function and known values for the correlation parameters, the maximin optimal designs are asymptotically d-optimal, and the minimax optimal designs are asymptotical g-optimal designs. So maximin optimal designs are those that maximize the minimum distance between the points that they belong in the design. So no two points are close together and they spread the points. And minimax designs are those that minimize the minimum distance between the designs, between the points in the design and the points in the design region. So, and we are going to have good coverage of the design region. The d-optimal designs maximize the generalized variance of the parameters estimators, and then g-optimal design minimize the maximum predictive variance. So for the prediction problem, g-optimal designs are more relevant. In our approach, we choose the square error loss function, given here, and we need to find the base decision, which now is given by y hat, and it's going to find the best prediction, and it's given by the mean of the posterior predictive distribution. So we evaluate the loss at the best prediction, and we ended up that our objective function is going to be the variance of the posterior predictive distribution average across the unknown data and the prediction points, xn plus. We assume conjugate priors for beta and sigma squared g, and now we are going to have two cases according to the assumptions that we are going to do about the correlation parameters of the Gaussian process model. So if we assume that we know the correlation parameters, then we are able to derive analytically the posterior predictive distribution and also the marginal distribution of the data, and this integral with respect to the data is analytically tractable. And this is what is common in literature. However, if we don't know the correlation parameters, then the posterior predictive distribution is not available in closed form. So this integral now is not analytically tractable, and we need numerical methods to evaluate it. If we are going to find a design, we need to optimize this function a lot of time. So this is computationally expensive, and for this reason we proposed an approximation where we decompose the objective function based on the law of total variance, and now the objective function can be split in two parts conditional on the correlation parameters. So the first part, psi1, is the expectation of the variance of the conditional posterior predictive distribution average across the data and the prediction points. The second integral is the psi 2 and is the variance of the mean of the conditional posterior predictive distribution. So the first part is analytically tractable now with respect to the data, but for the second part we need to approximate it, and we are not able to derive it analytically. So here it is a bias variance trade-off, and we can use Markov chain Monte Carlo simulations and Monte Carlo integrations to evaluate psi 2, and in that way we are going to have low bias but high variance and high computation cost. The alternative way is to fix the psi 2 equals to 0, and this is going to have potentially high bias but 0 variance and 0 computation cost. So in our approach we set the second part equals to 0, and now the objective function is approximate only from the first part, and the objective function is proportional to the generalized Greek invariance average across the prior distribution of the correlation parameters and the prediction point. So this saves us a lot of computational time because we are able to derive analytically the integral with respect to the data, and also we can use quadrature methods to evaluate the integral with respect to the correlation parameters phi. In order to set the second part equal to 0, we had plenty of numerical and theoretical evidence and some theoretical insights. So we perform a sensitivity study where we generate random designs for different number of points, different prior hyperparameters, and evaluate both parts of the objective function, psi 1 and psi 2, using simulations. So we always found that the first part, psi 1, dominates psi 2, and in fact psi 2 is very, very small and very close to 0. So the rankings of the designs are very similar under psi and psi 1. This numerical evidence led us to some theoretical insights, and we were trying to understand why this is happening. So the integrand in psi 2 depends on the posterior distribution of the correlation parameters, and we have the integrated likelihood times the prior distribution of the correlation parameters. So under some assumptions, the integrated likelihood is bounded by a polynomial of the correlation parameters. So for the case of lambda and tau square going to 0, where we have the case of high correlation, the integrated likelihood goes to 0 at faster rate. Also, we have some evidence from the literature where Yu and Kaufman, they also study the predictive performance with respect to different priors, and they also found that the variance of the mean of the conditional posterior predictive distribution is very close to 0. Also, Lederman and her co-authors, they propose a Bayesian integrated mean square prediction error as an objective function to find designs for prediction, and this criterion is derived from a frequentist approach average across the prior information for the correlation parameters, and our approach gives a proper Bayesian interpretation for this criterion as well. So the second integral now is with respect to the prediction points, because we don't know where we want to predict, so we want to integrate out this uncertainty as well. So again, it's a bias variance trade-off, and we can use a fixed grid, which is going to result to 0 variance but high bias and low computational cost, or Monte Carlo grid, which results in high variance and 0 bias and high computational cost. So if we want where we want to predict, we are going for fixed grid, and this save us time. Also, for special correlation functions, we are able to derive this integral analytically as well. So the first example is from the area of computer experiments, where we have a simple simulator of a helical compression spring. This simulator has three inputs: the wire diameter, the spring index, and the spring coefficient. And we assume a Gaussian process model with a linear mean function and a separable exponential correlation function. So by this, I mean that we are allowed to have different correlation in different dimensions. We have normal inverse gamma priors for beta and sigma squared g, and we are going to find Bayesian optimal designs for 10 points under two different priors for the correlation parameters. So we obtain these priors by analyzing data that we had from a Latin hypercube design. And the first prior, we have a deterministic model where the noise to signal ratio tau square is equal to 0, and uniform priors for lambda 1 and lambda 2. And for the third correlation parameter, we assume a very, very small value, but not equal to 0. In the second set of prior, we now include a noise to signal ratio tau square, and we let the correlation parameter lambda 3 to drops to 0. So this plot shows the two-dimensional projections of the Latin hypercube design, and the lower diagonal correspond to the Bayesian optimal design that we found under our criterion. We can see that for the first set of prior, so this one corresponds to the first set of prior and this one to the second set of priors, we can see that they have similar space filling properties, and the average distance between the points is 1.43 for the Bayesian optimal design and 1.40 for the space filling maximum Latin hypercube design. The average prediction variance for the Bayesian optimal design is 30% smaller than the space filling design. For the second set of prior, we can see where we allow the correlation in the third dimension to be equal to 0. So now we are allowed to have high correlation in the third dimension. The points collapse to the extreme. So this is because the design now is influenced by the linear trend and the linear mean function that we assume. Again, the Bayesian optimal design has 80% smaller average prediction variance compared to the space filling design. The second example is from the right optimization that I mentioned to my introduction. So, as I have mentioned earlier, we have different versions of the car that they have different mass properties and different right characteristics. And in our problem, we have 5 design variables, and basically each one of the variants, the version of the car, can be expressed as a function of these 4 variables. And we use the 5th design variable, the damping, as a tuning parameter, where we are going to tune the performance of the car, and so we are going to accept the right characteristics. So we have 10 different variants, and for each one of these variants, we want to predict the right performance of the car for given speed and given road surface, and also choose the best value for the damping. So instead of running physical experiments, we use a computer code to predict these 10 variants. We proposed a model-based design using with 33 runs, and this is the two-dimensional projections for the first 4 design variables, and the red points corresponds to the 10 version of the car, and the open circles are the optimal points, and we can see that they are concentrated around the points that we want to predict. And for the last one, because we don't have a specific points to predict, the design is a space filling design that tries to cover the area. The second example is from spatial statistics, and it's a two-dimensional example. So we assume a noise to signal ratio to be known, and we have a linear mean function and an exponential correlation function, and again we assume normal inverse gamma priors for trend and sigma squared g. Also we have a uniform prior for lambda, and we consider 4 fixed value for the noise to signal ratio. So the plot here shows initially the contour plot shows the average correlation between every point in the design region and the center, and the red color corresponds to high correlation and yellow color to low correlation. So as the noise to signal ratio increases, the correlation decreases, and the black dots corresponds to the optimal choice of the points. The range of the correlation here is 0.5, 0.4, 3, and 2. So we can see that for the first case, we don't have a measurement error. Tau square is equal to 0, so we have a space filling design. And as the noise to signal ratio increases, then the points start moving towards to the boundaries, and especially for the case of what have low correlation, the points are influenced from the linear mean function, and they are going to the boundaries. Then we extend the previous example by assuming a known noise to signal ratio, and we keep everything else the same, and we have a Matern correlation function and an exponential correlation function. Also, the prior information about tau square covers the 3 first cases of the previous example. So the contour plot shows the same as before, and the first one corresponds to the exponential and the second one to the Matern. We can see that for Matern with lambda 2 equals to 1.5, the correlation is higher, and also the range of the correlation is 0.3 here, and for the Matern is almost half. So when we are going to choose the points, for the exponential correlation function, the design is going to be somewhere between these two designs. So we can see that it's influenced by the large value of noise to signal ratio. Once we have Matern, we can see that the points start moving again at the boundaries, and this is because we have constantly high uniform correlation, and now because we have high correlation in all the design space, the distance between the points doesn't matter, and they move to the boundaries, influenced by the linear trend. Another way to see how the range and the degree of the correlation affect the choice of the design is using the density plots evaluate at the 4 quadrature points that we use. So this is for the exponential, and this is for the Matern. So we can see that for the Matern, the mean is always higher compared to the exponential, and the range is always smaller compared to the exponential. So the new model-based designs are a compromise between minimax and maximum designs, and the prior information that we have about the noise to signal ratio can lead to different designs. Also, the designs are depends very much on the distribution of the correlation, and especially on the range and the degree. Then we apply our methodology to a real example with the data that from the sensor placement problem, where we have again a linear mean function with low correlation, medium correlation, and high correlation. So the distance here, it was the geodesic distance, and we basically saw the same pattern as before. So again, the open circle are the candidate points, the blue are the optimal, and the black circles are the points that we want to predict. If we have low correlation, the optimal stations are at the boundaries of the region, so we don't have any points in the center of the region. Once we have medium correlation, we can see that there are points around the points that we want to predict. And again, when we have a high correlation, the points moves again to the boundaries. So the distance doesn't matter because we have constantly high correlation. And the last few slides is going to be from the estimation problem, designs for estimating the trend of the Gaussian process model. So we can have exactly the same decision-theoretic framework where we have the loss function, and the best estimate now is the mean of the posterior distribution of the trend parameters, and the objective function ended up to be the trace of the variance of the posterior distribution average across the unknown data. We had the same approximation. We ran again a sensitivity study. We had the same evidence that side 2 is very small, so we set that value equal to 0, and now the objective function is proportional to the trace of this matrix average across the prior information for the correlation parameter. So basically this criterion is similar to the A optimality. We apply this methodology to well plates, and where we have a model that we have the treatment factor indicated by S and the Gaussian factor indicated by X, and now we have a mean function that corresponds to the treatment factors and a Gaussian process that represent our the random effect for the Gaussian factors. We have a well plate with 9 fixed locations, and in each location we apply a different treatment. So we have a linear mean function, and then now the treatments that is -1, 0, or 1, and the distance between the well can be captured using a taxi cab distance and an exponential correlation function. So the aim here is to find the optimal settings for the treatments, but also where we want to apply these treatments. We have the same prior information as before. So in this plot, we have the 9 locations, and here we have the treatments. So for example, we choose this combination to be applied in this area here. Because it's difficult to interpret these results, and we don't know how to interpret these results, we generate 10,000 random designs with a different treatment allocations and applied in a different well, and we evaluate the objective function, and their values are given by the histogram here, and also we evaluate the objective function for the optimal design that we found, and it's always much smaller compared to the random procedure. So it matters to choose where we are going to apply the treatments and which treatments we are going to apply. However, in estimation problems, we have identifiability and consistency problems. This is known from Kennedy and O'Hagan paper, where we don't have any of these problems when we have prediction the aim is the prediction, but when we are going to estimate the trend parameters from a Gaussian process, then we have identifiability issues. In order to overcome this issue, we can modify our correlation function by making the mean function orthogonal to the Gaussian process prior. So we can use the same methodology, but changing the correlation function now to incorporate the orthogonality condition and find optimal designs for estimating the trend parameters. So to summarize, we propose a model-based approach for choosing the design points for a Gaussian process model, where these designs are usually tailored for prediction and take into account the uncertainty about the unknown parameters. These designs are strongly influenced by the degree and the range of the correlation, and also from the choice of the mean function. However, they are largely insensitive to the choice of the prior hyperparameters for sigma squared g, and is a general methodology that can be used to different application areas. Also, we have tried to apply this methodology to robust product designs, and for example, in the Jaguar Land Rover example, where we have the damping as a tune variable, we can find the optimal value for the damping that is going to introduce the minimize the variance that is going to be introduced due to the other design variables that I have shown to the table before. So we can use a model-based design approach to find out robust product designs. Thank you.
I mean, completely miss the point, right? But are you running into risk of, by using your prior to do your optimization of the node, to actually bias your results even more towards your prior information? I mean, you have some kind of model deficiency here. Is not this risky to actually optimize your nodes, using your prior?
Yeah, but sometimes you have prior that is available, and you can use it, so you can define the prior hyperparameters and take into account that prior. So this is the idea of a model-based approach, that you can incorporate any available prior information through these prior distributions, and then make the design tailored to that.
You may have a prior that is almost right, let's say, that is more or less what people believe is the prior, but it's not actually the prior. So are you running into risk of, making your things optimal to something that essentially is wrong?
Okay, you can then do some sensitivity study according to the prior hyperparameters and see the design, how it's going to change, and trying to make it robust to this prior information. But we have seen that the design basically change between minimax and maximum design, so spreading the points around, trying to coverage.
Since you are basing that within the Bayesian risk framework, and since you are using the squared loss as your loss function, I think when I compare this with a naive and greedy entropy-based design, in your method you need more simulator calls than entropy-based design, because in an entropy-based design it only needs the variance. In this case you need the posterior predictive of the mean function as well as the data. So
but
on a grid, you in a greedy entropy-based design, you actually need less number of simulator call.
But the entropy doesn't need to capture again the distance between the predictive distribution.
No, so that's why I'm asking, have you my question is, have you compared this thing with the entropy-based design?
No, I haven't compared it with the entropy-based.
Okay.
This is something that we need to do.
I've done quite extensive work in this area, and I said in my talk on the first week that you're right in the sense that what happens is that the design is trying to be a classical design with respect to the first few cardinal wave functions. So if you have a linear thing, then it'll put it.
Yeah.
So the less weight is put on the early cardinal wave,
Going to be more
the
specific.
more it will spread out.
Yep.
That's the basic principle. So if correlation, dies off slowly, then it will spread out, and that's typical of all optimal Bayesian design.
I think interestingly also
Yeah.
the correlation stays uniformly high.
Then again, it's doing
It
the
will
same thing.
also-
Could I make one more point? And that's that in a lot of the work you have this risk, which is like the integral of the risk, but there are a lot of other functionals that you can put on the prior distribution. For example, you could take the maximum, the pre-posterior expectation, which you've got
Yeah.
right, of the maximum of the posterior. So, there's a lot of other functionals rather than always integral of the
Yeah.
loss
And save us
function, because that's,
time.
that's try some other
Yeah.
interesting functionals. You could take double integral and take Rene entropy, which would be, more like a variance.
Okay, yeah. And then we can compare it with this. Okay, yeah.
The power of the Bayesian decision-theoretic approach is really that when you've seen your first 10 design points, you'll then decide, well, do I need 10 more, or am I ready to go ahead and build the car, or, am I done or something? And so in some sense, you're going to, now that you're going to decide whether to design more and how many and where in the future. And almost I really wanted you to get onto so I've run 10 and I've got what I've got, now what do I do? And does that influence what I should do at the start? And I wonder if the results will be the same.
So this is so there are cases where you have a fixed number of runs, so you have to do it within this number. Or an alternative, you can use a sequential approach and have these 10, and then based on the information that you have from these 10, you can go forward and add more points.
If you have 10, is the best thing to do to just run 10, or is the best thing to do to run 5, do some calculations, and then decide where to run the next one?
If you are sure about your prior information, then run all of them, the 10, but if you want to look at, then you may need to have like 5 and then add another 5. Depends from the problem, I think.
Are you sure of your prior information? Sorry, just to ask, do you mean that the posterior would be the same as the prior?
No, I mean, like, for example, you know what the correlation represents, and if you have high correlation or low correlation, and you can choose these from your prior hyperparameters.
In the spatial statistics one, how much information can you give to your design? Do you take into account the land features in this correlation?
No, this is another, it's more complicated, because if we want to take into account the landscape, maybe we don't have isotropic Gaussian process, so we need to take an isotropic function. That was the simplest thing that we do for that example. Yeah, but we need to take that into account.
Does it seem to put them all out on the
Yeah.
coast and on the opposite coast?
But this is because it's from the correlation, because it was high and move the point, so the distance in your Gaussian process didn't change.
Just a quick one. I mean, there's quite a lot of work on empirical kriging. You base your design on multi-stage, or you base your design on empirical estimates of correlation function first, particularly used in environmental situations. So there's quite a few papers on that, answering that very point.
Okay, I think we're going to end it there, and thank Maria.